Hello again. Today we're going to be talking about related rates. Related rates are usually word problems, but sometimes they can just be simple equations where you're given an equation that contains more than one variable. You're given the rate of change of one variable, in other words, the derivative of one variable with respect to time, and you're looking for the derivative with respect to another variable with respect to time. Let me just jump right into an example. So let's say we have the equation x squared plus xy is equal to, let's say, 6, and we're given the x dt is 3. We are trying to solve for dy dt when x is 2. So this is your typical setup. You're given one rate, looking for another rate. You have some equation that relates your two variables, the x and the y, and you're usually given the value of one of your variables at some point in time or some situation or arrangement. Okay, anyway, so what we're going to do is we're going to implicitly differentiate this equation with respect to t on both sides. So because neither of our two variables, x or y, is the variable t, we have to apply the chain rule to both of those. If you remember from last time, one way to describe this is when you take the derivative with respect to t of x squared, first just take the derivative with respect to its own variable x. So you get 2x. And then times, by the chain rule, you take the derivative of the inner function, which would be the x, with respect to the original variable, t. So it's going to be times dx dt. So when you take the derivative function of x, just take the derivative normally, like with respect to x, and then put dx dt after it. Okay? You have to be a little bit careful when you have a product of two functions like x times y here. You need to be applying the product rule. So the derivative of the first, derivative of x would be 1 dx dt. So that's the derivative of the first times the second plus the first, which is just x, and then times the derivative of the second, which is going to be 1 dy dt. And the derivative of a constant is 0. Great. Okay. Now at this point, we can try plugging in what we know and see if we can solve the problem yet. So we know that x is 2, the x dt is 3, the x dt is 3 again. We don't know why. Okay, we know x is 2, and dy dt is what we're trying to solve for. So we're missing one piece of information. We need to know y. Once we know the value of y, we can then solve for dy dt. So to get the value of y, just take your value of x, that x is 2, plug it into the original equation and solve for the other variable, in this case y. So over here to the side, plugging 2 into that equation would give you 2 squared, which is 4, plus 2y equals 6. Therefore, 2y equals 2. So y equals 1. Great. Now we know that this y is 1. And now we can solve for dy dt. 4 times 3 is 12, plus 3, plus 2 dy dt equals 0. So dy dt is going to be, well, that's 15, so subtract 15 and then divide by 2. So negative 15 halves is our answer. Okay. Next, let's do an example where the problem is your more typical word problem. Okay. So I'm not going to write down the word problem word for word, so just follow along with me. Okay. Let's say that we have a ladder. It's leaning against a wall, and we know the length of the ladder. Let's say it's 10 foot long. Okay. So you might want to start drawing a picture. So here's my wall, here's the ground, and here's my ladder. And they said the ladder was 10 foot long. Let's just put a 10 there. okay? Then we know the top of the ladder is sliding down the wall at a rate of 3 feet per second, okay? So what you want to do on your picture is let's label this length a variable x. And since I said it was going down the wall at a rate of 3 feet per second, that means that the rate of change of x with respect to time, in other words, dx dt, is -3. Negative because it's decreasing at a rate of 3 feet per second. Okay. We are trying to solve for how fast the bottom of the ladder goes away from the wall. So let's call this length y. So we're trying to solve for dy dt when, let's say that when x is 8. Okay, so I believe that's enough information to solve the problem. Okay, so what we're missing this time is we don't have an equation that contains the two variables we want, x and y. So we need to figure out what equation to use on our own. Well, looking at the diagram and realizing that's a right triangle, all of our variables and our constant are all the different sides of a right triangle, so we can apply the Pythagorean theorem. So x squared plus y squared equals 10 squared, which is 100. Okay. Now we implicitly differentiate both sides with respect to time. I'm just going to put this little arrow in ddt. So the left side becomes 2x dx dt plus 2y dy dt. And then the derivative of 100 is 0 because it's a constant. Okay. We're going to need to solve for y before we can plug in and finally get our answer. We know x, but we don't know y. So plug x into here and to solve for y. So we get 8 squared plus y squared equals 100. Well, 8 squared is 64, so if we subtract 64 from both sides, y squared is 36, and therefore y is +6. Note, when I square rooted both sides, I didn't bother to put plus or minus, because I know I can't have a negative length. Okay, so y is 6, great, now we know everything we need to know. X is 8, dx dt is -3, y is 6, and then we're solving for dy dt. So let's divide by 2 everywhere. That'll just simplify the problem. And then this times this is -24. I'll move that to the opposite side of the equal sign as +24 equals 6 dy dt. Therefore, dy dt is 4. That means the bottom of the ladder is sliding away from the wall at a rate of 4 feet per second. Okay. Let's do another related rates problem. This one will also involve triangles, but it won't be a Pythagorean theorem problem. This is another really common problem, the one I'm about to give you. We have a lamp that is on top of a pole, like a street light, okay? Let's say the pole is 15 feet tall. We've got a man who is, let's say, 5 foot tall, and he is walking away from the light with a speed of 7 feet per second. 7 feet per second. Well, that's awful fast. Let me make it more realistic. Let's say that he's walking at 1 foot per second. Okay. The question is, how fast is the length of his shadow growing? Okay. So first we have to figure out where the heck his shadow is. What variable, what derivative is this tied to? The rate of change of what variable? So first for this, if we call the distance between the person and the ladder x, that is dx dt. It's how fast he's moving away from the ladder. So dx dt is 1. Okay. Next, let's figure out where the shadow is. Well, light is coming off of the top of this pole, barely going over his head, and would hit the ground right there. And anywhere to the right of that, light is going to be able to get to, but anywhere from here to here, light from the lamp is going to get blocked by the person, creating a shadow where the light can't get to. So this dark region is his shadow. The question was, how fast is the length of his shadow growing? So let's call the length of his shadow y, and we are trying to solve for dy dt. This time I don't need to say like when x is 5 or when y is 3. It turns out that dy dt will be a constant for any value of x or y. Okay, so I've got right triangles. You know, that's a right angle, that's another right angle. But I'm not going to use the Pythagorean theorem because I don't know anything about either of these two hypotenuses. Hypotenuse? Well, whatever. Plural of hypotenuse, I don't know what that is. Okay, anyway. But, you know, we have two different triangles. Let me draw them. The big triangle is 15, and the length is x plus y. The other triangle is 5, and this length is y. And this angle is the same for both of those triangles. That makes these two triangles similar, and so we can use facts that we know about similar triangles. What I'm going to use is the fact that the ratio of any two sides on one of the similar triangles is equal to the ratio of the appropriate sides on the other triangle. Therefore, I can set up an equation, x plus y over 15 equals y over 5. Before we implicitly differentiate, I would like to simplify this equation. Note I could multiply by 15 on both sides. And the 15 divided by 5 is just 3, so x plus y equals 3y. Let's subtract y from both sides, and we get the very simple equation, x equals 2y. Now we implicitly differentiate that with respect to time, and we get dx dt equals 2 dy dt. And then we simply plug in the rate we were given, that was 1. Therefore, dy dt is a half. So the length of his shadow is growing at a rate of a half of a foot per second. Okay, so there are many other related rates problems that you could have, and depending on the problem, you may need to remember some formulas, like you may need to, remember what the surface area of a sphere is, or the volume of a sphere, or the equation for a cylinder. So you may want to go and review formulas for different geometric shapes, because they may pop up in these problems dealing with the related rates. Problems dealing with triangles are often the Pythagorean theorem, similar triangles for this type of shadow problem. And you might end up using just the definition of sine or cosine, maybe if one of your rates is the rate of change of the angle, like d theta dt. Okay. One last note, on these related rates pictures that I draw, I only label constants like the 5 and the 15 for things that are truly constant, that are never changing. Like the length of a ladder doesn't change, so I labeled that, the length of the ladder 10, I believe it was. Here, the length of the lamp and the height of the person, neither of those are changing, those are constants. Anything that's a variable that is changing, label with a variable. Now, you don't want to just label everything like, I guess this is changing, that's a variable, but we're not interested in the distance from here to here, so label anything that, rate or are looking for with a variable, but never write down a constant in the place of something that's actually a variable, because it may get you confused. It may make you think that it's actually a constant. So like an example, the sliding ladder problem, drew the ladder. The length was 10 foot for the ladder. And then eventually I said, like, find the rate of change of dy dt when x was 8. But I didn't label 8 on the diagram. I wrote that over here to the side that x is 8. So anyway, just a little warning or a tip, so don't write down numbers on your diagram that aren't constants. Okay, so that's going to be it for today's video. See you next time. Thank you. Bye-bye.